Good morning, everyone. We're going to get started here in just about a minute. I just want to remind those of you that have just recently joined, we posted a Google spreadsheet in the group chat to serve as a sign-in sheet. We want to try to keep track of who showed up to the Zoom meeting this morning, and we do plan to still send out certificates following the training, so y'all can still get some CEUs. So if y'all don't mind following that link and signing in just sometime throughout these presentations, then we'll make sure we'll send those certificates out following the meeting. And I'm gonna post it again just in case for people who sign on after I shared it the first time can't see it. Well, so my name is Claire. I'm with the Texas Water Resources Institute. I've been the one emailing you, and I really appreciate y'all signing in virtually today. We obviously wish that we could be there in person with y'all to host this training, but we appreciate y'all's flexibility as we try to make sure that we're following proper CDC and AgriLife guidelines to keep everyone safe through all of this uncertainty. So we really appreciate y'all working with us. With that being said, this is also the first time that we're doing a virtual training like this. So I'm hoping it will go smoothly, but just bear with us as we kind of work through this first time. And I hope it's going to be a good morning session for you all. I'm also recording it. So if for some reason your internet jumps off or we have any technical difficulties or you need to run out before it finishes, we are recording it. So my hope is to be able to share it with y'all following this training. As well, just since there are several of us online, if y'all have questions as we go through the morning presentations, if you don't mind writing them down in the group chat, and then once the presentation is over, I hear that it's very difficult to hear me. Let me try to turn up I'll try to get closer to my mic and turn it up. Hopefully this is a little bit better to hear me. I'm just working off of my laptop. So if you guys have questions or comments, I see y'all have already found the group chat box. So just to make sure to write those questions that you might have during the presentations, and then we'll try to address them at the end of the presentation. And then I think everyone is on mute, but if you could just keep your computers or your mics on mute during the presentations to help with the recording so that we don't have any additional feedback, that's also appreciated. So with that, I'm going to share my screen. And get started. Okay, so to start off, we want to just offer a brief introduction to this program and just the idea of natural riparian corridors and natural stream restoration. So just for some general background, the US Environmental Protection Agency did a study back in 2013 and found that over half, about 55%, of the river and stream miles in the United States were reported to be in poor condition. And a lot of that was due to having streamside disturbances and poor riparian vegetative cover. And the reasons for having poor riparian vegetation and those disturbances, it did vary. It can be both natural and anthropogenic, but one of the more important stressors that they noted was the increase in human population and kind of the demand that put in our watersheds with the increase in industrial, commercial, and residential development, and how that could be linked to poor vegetative cover. And when we see these systems in a degraded quality, we see that there's poor water quality, so we're seeing higher bacteria, nutrients, and sediments entering into our stream systems. There's not as much diversity in in-stream habitat, so we're also seeing less terrestrial wildlife due to the lack of good habitat, and then a decrease in diversity of your aquatic species. So just an overall decline in the stream health. So a lot of what we work at AgriLife, and as also several of the agencies y'all work at, trying to combat. And so when we see these unhealthy watersheds, we're seeing that a lot of our floods are becoming increasingly more damaging as we're getting that higher volume of water coming into our systems, overwhelming the systems during those large storm events. It's also causing lower base flows. So it's when we're separating from that water table, we're not seeing that sustainable base flow that we have even during the summer months when it's drier. It's also bringing in higher sediment loads, which leads to reduced reservoir storage capacity. And I'll talk about that more in a few slides, but that's affecting some of our water sustainability. It's also bringing in the invasion of exotic species, the loss of natural riparian habitat, and that degraded water quality that we want to try to combat. And so as I mentioned, one of those big stressors is the increase in population. And this is something that's happening nationally, but since we're here in Texas, we want to focus on kind of that increase in population here in the state of Texas. So this is a study that was done from our sister agency at A&M, the Natural Resource Institute. And what they did was they looked at the population of Texas from 1997 to 2012, and they mapped it out on the county scale. So they saw about a 36% increase in population over that time period. And what they found when they mapped it out by county, that the majority of people were already moving to our top 10 highest populated counties. About 65% of the increase was going into those highly populated counties. And you can see that on the graphic here. So the deeper the reds, that's the higher the population increase. And you can see it's in our San Antonio, Austin 35 corridor, up in the Dallas, Fort Worth Metroplex, down by Houston, South Texas, and then out to El Paso. So this increase in population doesn't happen uniformly or evenly distributed across Texas. And so when they saw that population change, what they did at the same time was also look at the loss of rural working lands over that same time period. And when they looked to see where that rate of conversion was happening, they saw a lot of that was linked to those areas where we're seeing that increase in population, where we're losing some of those rural working lands, and a lot of times those cities are getting built out. So we're building more parking lots, more buildings, residential areas to support that increase. And what happens is then that's changing the look of our watershed. So we're losing those rural working lands that had good vegetative cover, healthier soils that are going to be able to absorb a lot of that water and slow down that flow of water, especially during those storm events. And a lot of times making it impervious as we're building streets and parking lots and buildings. So then that's not going to be able to soak in and absorb that storm water. So now it's just going to be running off of your system. And so when we see that, that's one of those drivers for these increasingly damaging floods that we are especially seeing in our urban areas, because now during those storm events, we're not going to be able to capture as much water on site. So we're going to be having a higher volume of water moving faster, and it's going to be causing a lot more damage during those larger storm events in the cities. And I think all of us that live in these urban areas around Texas, we kind of have seen some of the effects of flooding in our areas. The other effect of having poor riparian areas and the change of our watersheds from the increase in population is that when we have that higher volume of water and when it's moving faster and you don't have that good vegetation that's slowing down the flow of water and helping to protect those banks, is that we increase the amount of erosion along the stream system, the erosion along the banks. And so when we're having more land that's falling in with those higher erosion rates, then we're losing land that we could be using for other purposes. It's going to lower our property values. It's also a risk for human safety. We don't, especially in our more public areas where there might be a lot of erosion. And when we have all of that excessive erosion, we have more sediment that's entering into our stream systems. And so when that sediment, the excessive sediment, gets into our streams and then it's going through the river, once it hits a reservoir or a lake where that fast moving water then slows down, that sediment starts to be able to settle. And as it starts to settle, it's going to start reducing the storage capacity of that lake or reservoir. So, some erosion is natural, but when we have that excessive erosion, that's when you start getting more and more sediment entering into our stream systems, and then it starts settling and reducing that storage capacity. And that's an issue because as our population continues to increase and we want to make sure we have a sustainable water future, have enough water for all the different needs that we need here in Texas for both humans, industry. We want to make sure that we can protect that. And so the Texas Water Development Board predicts that our surface water supplies are going to decline by about 3% in the next 50 years, specifically due to this sedimentation reducing our reservoir storage capacity. And 3% might seem like a smaller number, but that's roughly the amount of water that can supply a family of 4 in 1 year. So over 231,000 homes that are a family of 4 in 1 year would be the amount of water that we're losing. So that is a lot of families that we want to make sure that we can protect that as we move to the future. And unfortunately, right now, there's not a lot of great strategies for how to combat some of this sedimentation that we're seeing. So the Texas Water Development Board also noted that sometimes the dredging, so kind of trying to remove that sediment from that reservoir once it's already in there, can be just as expensive, if not more expensive, than just building a new reservoir completely, which isn't exactly the best option either, to build a whole new reservoir instead of being able to remove that sediment. So several areas, such as the city of Austin, have found that being a little bit more proactive. So instead of trying to spend all this money or trying to figure out how to improve this, once that sediment has already entered into the reservoir and already has started to reduce that capacity, what can we do to prevent it from even getting to that point? And so what they found is by improving their floodplains, providing that good vegetation, um, and to help stabilize those banks can help capture some of that sediment and then reduce the amount that's entering into our streams and creeks. So that's going to save money in the long run. So you have to put out more money in the beginning, but it's going to save you money because you're not going to have to build a new reservoir or dredge it after it already becomes a problem. So kind of all of that has brought us to why we wanted to start offering this program. Dr. Jabber has been doing these programs up in the Dallas area, but we really wanted to bring it statewide because a lot of these issues are what we're seeing around all of our urban areas here in Texas. And we want to kind of promote the idea of doing stream restoration, but also making sure we have some of these ecological benefits of having these healthy riparian areas and these healthy stream systems. And so we do that by offering these educational programs, but we also have a demonstration site in Seguin, which I'll talk about in a few slides. So these programs traditionally are one-day trainings that we kind of try to focus on the urban areas because that's where we're seeing a lot of stressors and a lot of changes in our systems. And so we're at the end of our first 3-year grant for this. So y'all, we're going to be our second to last one-day training. We were going to have another one in the Woodlands. It looks like we're going to try to do that one virtually as well. And then we were going to do an advanced 3-day training to really delve into a lot of these natural stream restoration techniques that Dr. Jabber will talk to you all about this morning. And right now we have that tentatively scheduled for May 12th to 14th. As we kind of learn more about this situation, we'll kind of assess if we need to postpone that date till later in the summer or the fall, or if we're going to have to try to offer some of that virtually. So we'll definitely keep everyone who's on this call, who signed up for this training, in the loop as we figure out what we're going to do with that 3-day training. I also want to note, while it's the end of this 3-year program, we have received additional funding to continue to offer these trainings for another 3 years. So I think our plan is to come back to Austin and the Woodlands, the 2 trainings that are going to be affected this spring, in the fall, to try to hopefully be able to offer a program in person, so you would get the full experience with the outdoor portion. So we'll make sure to email y'all once we get those dates set, but we do plan on coming back to the city to hopefully do the full program. These are generally geared towards professionals interested in doing restoration projects, consultants, landscapers, city officials, but we offer it up to anyone, and there's a lot of good information you'll learn throughout the morning that you can apply on your own property or in your areas. We hope that by the end of this, you're going to understand kind of the impacts of development on urban streams, specifically being able to recognize what a healthy and a degraded stream system looks like, be able to assess and classify a stream using the Bank Erosion Hazard Index, and then understand the difference of when we talk about natural stream restoration, what that means versus the traditional stream restoration techniques. So this is the training outline that Dr. Jabber will go through this morning during his presentation. So he'll show this to you again and go into much more detail, but I just kind of wanted to throw it up to let you all know what you'll be learning about throughout the morning. And then so the other part of this, besides doing these educational programs, is we really want to be able to, have a demonstration site where we can hopefully show that some of what we're teaching, some of these benefits that we're talking about. So what we have is we're working with the Guadalupe Blanco River Authority, the Irma Lewis Seguin Outdoor Learning Center, and the Geronimo Alligator Creek Watershed Partnership. And we've set up a control site and a treatment site on the Geronimo Creek, where we've done natural vegetation on 100 feet of the bank, and then we left a site that we didn't vegetate, and we're monitoring both to hopefully show that by having that good natural vegetation is going to help reduce sediment from entering into the creek and help reduce some of the erosion rates along the banks. So kind of the hope is for some of these areas where maybe you don't need to do a full engineering project where it's only moderately eroding, maybe you can look at just doing some of these low costs, like adding in more natural vegetation, good stabilizing vegetation, as a more cost-effective way to help kind of restore these areas. So this is an aerial view of our treatment site. So you can see we've got 100 feet section that we've revegetated both sides of the bank, and then we've got about 100 feet buffer, and then we have a control that we have just not done anything with. We haven't done any planting. These are pictures before planting of what our treatment site looked like. So you see that it was pretty much just some weak grasses. There were some elephant ears that we left in place for a little while as our other vegetation set, and then we sprayed to try to remove some of that. And then here's a picture of our control site down at the Outdoor Learning Center. And so what we're doing is we're sampling for total suspended solids within the creek. We do that quarterly, as well as during storm events that produce 1 inch of runoff. We're doing cross-sectional surveys, pebble counts, and we do those annually just to see how the profile of the stream channel changes. And then we're also have erosion pins and the Bank Erosion Hazard Index that we do quarterly to look to see how if we're having a lot of erosion or if we're slowing down erosion, comparing the two sites. So this is a look. We have ISCO set up to capture storm events, and then we take it to GBRA to do the analysis for TSS, as well as we do grab samples quarterly during our quarterly monitoring. And so we have these ISCOs set up at the start and at the end of each of our treatment and control sites, so we see how much is coming in and how much is leaving the system during each of those events. We also, at each of the treatment and the control site, we have 4 cross sections that we measure annually to see the change in the profile, as well as we do pebble counts. And we will talk to y'all more about what the cross section and the pebble counts are later in the day, but we won't actually be able to do them today. but we are doing those here at this site, as well as you can see in the pictures, we have these erosion pins that we set up and monitor quarterly. So we have about 6 inches that are above ground. And so when we go out, we measure to see how much is above and if it's eroding more, and then we'll knock it back in. So just 6 inches is showing again. And so we'll do that at each of the cross sections quarterly on both the treatment and the control site. So what we hope to show is that by adding in that good, healthy vegetation, by providing some of those natural services, it's going to provide those ecological benefits that we want. It's going to help dissipate the stream energy, so it's going to help to slow it down. And by slowing down that flow of water, especially during those storm events, it's going to help stabilize the banks more, so that's going to reduce some of that excessive erosion. We're going to be able to trap more sediment, and being able to trap that sediment, it's going to allow us to build and enlarge the floodplain. So that's going to give us better water storage capacity. It's going to help slow down that flood water. And when we're able to store more water on the land, it's going to allow for some groundwater recharge and also allow us to sustain the base flow, which is especially important during those summer months when we're not seeing as much rain, to be able to still provide that water. And so when we have a system that's doing all of that, slowing down the flow, trapping sediment, recharging groundwater, what we see is we see a lot of those values that we want. We see improved water quality. We're seeing enough water quantity to be able to support aquatic species, habitat, and forage, as well as for whatever uses we would like. It also has good recreational value, which especially here in Texas, we value so much, and that overall aesthetic beauty. So really trying to show that by planning to have the system function to do all of these things gives us those values that we really want, and as a community can get behind and understand why it's important. And so riparian vegetation is really the key to this. It has so many benefits by having those good deep root structures to help stabilize those banks. It also can help clean and trap sediment and other pollutants before it enters into our creek. So you can even see in these 3 pictures, these are 3 different stream banks around Texas, and you can already start to see just how they might function differently during those larger storm events. The one up on the top left, where you've got a lot of diversity of vegetation and age classes, that one's going to be able to do those physical functions, to slow down that stream flow, stabilize those banks much better than the one on the bottom right, where there's pretty much nothing there to slow down that flow or protect those banks. And then up on the top right, you have a good buffer to help kind of protect that stream system. And so what we really try to show is, even though we call it a watershed, we want to think on a watershed scale, we really don't want water to be shedding off of our landscape. And as much as we can, we want to make our watersheds a water catchment, where we're going to be able to capture more of that water on site and to slow down that flow, and also be able to pick up any pollutants or sediment as it comes off of the landscape. And these water shedding and water catching systems, you can see right along the stream banks as well. So here up on the top left is, this is, I think, from excessive grazing on this property, but you can see there's really nothing protecting those banks or that stream system during any large runoff events, as opposed to down on the bottom right, where that's going to really be able to slow down that flow and help protect those banks more. And so we really see it as an overlooked opportunity, because when we don't have that good, healthy vegetation where we're able to capture that water on the land and be able to recharge our groundwater and sustain that base flow, then we're really just losing that water and not being able to use it for the benefits that we want. So making sure that we're managing these systems appropriately to be able to capture and store water is so important. And there's a lot of other benefits that come when you're managing your stream systems for these healthy riparian areas. As I mentioned, it's going to improve water quality. So we're going to see less bacteria, nutrients, and sediment entering into our stream systems. We're going to see lower in-stream temperature. It's going to improve our dissolved oxygen levels. It's going to which improves aquatic habitat and also allows for a better diversity and a better habitat for those macrobenthos and those fish communities. And so that all leads to making sure that we're improving and protecting our water quality of our existing water supplies here in Texas. This is something we work a lot with at the Water Resource Institute, as I know many groups do around Texas. So I just want to touch briefly on how we see some of this vegetation improving some of our water quality issues here in Texas. So the state, the Texas Commission on Environmental Quality, every 2 years, they will assess all of the monitoring data that they have for streams around Texas. And what they do is they look within the last 7 to 10 years and look for the monitoring where they have enough monitoring data to do an assessment. And then they'll check to see if those, based on what that designated use is for that water body, if it's meeting its associated water quality standards. And I'll talk about designated uses and those standards in the next couple slides. But just to show you, so 2016 is the most recent accepted report that has been released from the Texas Commission on Environmental Quality. And they were able to assess about 1,400 water bodies that had enough data from the last 7 to 10 years. And so what they found was about 574 of them were not meeting their designated uses and those water quality standards associated with it. That is actually a decrease from the 2014, so about 15 segments got delisted from the 2014 report, so we are seeing some getting taken off, and that's for a variety of different reasons as we get more monitoring data, but also we have a lot of people working on these watershed protection plans and total maximum daily load implementation projects around Texas to address a lot of these water quality problems. So and usually we always try to invite some of these watershed planning people to come to our programs because we see what their goals are to improve water quality are very closely linked to what we're trying to do by promoting more natural riparian habitats and stream restoration. We won't have a presentation on that today, but there are these projects that are happening around Texas and working to combat some of these water quality issues. Just in general, bacteria right now is the main cause for impairment on those water bodies. So we've got 39% of them that are impaired for bacteria. Next is low dissolved oxygen, which is usually attributed to high levels of nutrients, and then organics and fish tissue. So this is a look at the designated uses that are set by the state for each water body. So whether it's supposed to support a high or low level of aquatic life, then if it's going to be, then they're going to be looking at water quality standards for dissolved oxygen, toxic chemicals, total dissolved solids. For recreation, the main thing that they're testing is for bacteria. And then for drinking water and fish consumption as well, they have their own host of water quality standards. So based on that designated use, when they're looking at that monitoring data, they're looking for those specific water quality parameters to see if it's meeting that designated use. And so here's just an example for the water quality standard for high aquatic life. So you can see for some of them, it just has to be above or below a certain number. Sometimes it has to be within a range. But so all of these really vary based on what your designated use is for that water body. And then for some things like nutrients, we don't have set water quality standards yet. So they do have some screening criteria to let us know if this might be an area with high nutrient loading into your streams. And that's something that they are working on getting some standards created. We just don't have those approved yet. And so this is a look at some of the watershed-based planning that's happening around Texas. So you can see it's not just generalized to one specific area. People are working on water quality issues around Texas. And so when we go to a lot of these urban areas to do these trainings, there's usually always a project close by that we can call on to have come in and talk to us about some of the work that they're doing in the area. And so the main thing that they look at when trying to put into these plans to improve water quality is they're looking at point source and non-point source pollutants. And so point source, as the name kind of alludes to, It's a lot of times coming from a pipe, but it's really something that you can kind of point to and say, that's where this specific thing is entering into our creek, into our stream system. And so that's kind of, your wastewater treatment plants, your industrial facilities, your confined animal feeding operations, where they're discharging something directly into the creek. And for point source pollutants, you do need a stormwater permit to be able to discharge into the creek. So it does require a permit from the state that has monitoring requirements, as well as they get audited every several years from the state to make sure that they are meeting those standards that are set out in their permit. So there is some regulation that goes with those specific pollutant sources. For the other one that it's a little bit harder is the non-point source. So if point source, you can actually point to something. Non-point, there's no one specific area where that pollutant is entering into our system. It's more diffuse off of the landscape, kind of just during those large runoff and storm events where it kind of can just gets picked up and entered in, but not one specific spot. So that's kind of a lot of the pollution from your urban areas. There is a little bit with stormwater permitting now to try to kind of regulate some of those pollutants, but anything with wildlife, feral hogs, livestock, especially if they're spending a lot of time in and around the creek, have a risk of defecating around the area and can cause increased bacteria levels. Crops, if you're not using your fertilizer or pesticides appropriately, you're using too much or using it at a wrong period of time, can be non-point source pollutants. And then on-site septic facilities, when they're not being maintained properly, have a risk of polluting your stream systems as well. So for these, since they're not one specific area that it's entering, it's a little bit harder to regulate on a state level. So for the most part, we really try to focus on reducing the risk of those entering into our stream system. So a lot of these plans talk about how to maintain your septic system so that it's functioning properly. Proper fertilizer and nutrient management for not just agricultural areas, but also for homeowners and cities. For if you have livestock on your property, proper rotation of it so they're not spending as much time in and around the creek. So all of those different management measures to try to reduce some of that, again, being proactive and reducing it before it even enters into the creek are kind of the key things. And then again, for us, by having that healthy riparian area, that good vegetation around your stream, that just adds as one extra layer of defense to be able to kind of capture any sediment or pollutants that might be coming off of your landscape before entering into your stream system. So that's why we feel there's a good partnership between what these plans are talking about and what we work towards in our programs as well. So with that, our stream systems, if it's not the most, it's one of the most important natural resources here in Texas. It's going through not only our cities, but rural areas, private lands, public lands. So it really takes a concerted effort by everyone to make sure that we're protecting these natural resources. So that's why we feel it's important to host these educational programs around Texas to make sure that we're all doing the best we can to protect our stream systems and our water. So with that, I'm going to close out, and then I'm going to stop sharing just so I can see if there are any questions. If y'all have any right now, you can feel free to write them on the group chat. I'll give a couple minutes. If not, then I'll have Dr. Jabber switch over and he'll start his presentation.
Claire, one of our questions was repeating the site where the Seguin demonstration was, and I included that on the group chat, as well as the website link where people can go to see more information and the pictures over time for the demonstration site.
Oh, okay, perfect. So you included that information?
Yes, it's in the group chat with the link.
Okay, perfect, thank you. And when we send out those emails at the end, I'll include all those links again. So then with that, I'm going to mute myself and hand it over to Dr. Jabber to talk to you about natural stream restoration.
Wonderful. Thank you very much. So my name is Fuad Jabber. I am a faculty with the Texas A&M AgriLife Extension and the Biological and Agricultural Engineering Department of Texas A&M. Couple of things. I did lose internet for a couple of minutes when I was when Claire was talking. So if I get lost, stay online, and I'll probably be able to get back. Because there's a lot of pressure, a lot of people working from home, and two, I have children running in the house. So at any moment. Okay. So let's start. So we're going to talk about urban riparian restoration and stream processes. And so this is, Claire did show you that slide, and basically we're going to talk about how streams form, their role in nature, and then we're going to go into a methodology to classify streams so we know how to approach any restoration project, what causes instability in streams. This is the hydrologic cycle, and you can see this is a complex process with the streams. What's the role of the streams in that whole cycle? Basically, once rain falls on the ground, it's flowing along the slope toward the low-lying areas, and as a result, it starts accumulating in these low areas. And with time, based on a pattern of rain events that's related to the climate, the water starts creating a channel for itself, and that channel forms and it forms based on that rain pattern. And as different channels meet, they become larger and larger, and they bring back that water to the ocean. And so that's basically the water function of a stream. There's another function of a stream that's very important, is that it also carries sediments. It carries sediments from the upper areas, from the mountains, and the sediments flow in the river and are basically distributed along the river stream to form different landform, including beaches, before it goes back to the ocean. Responsible for the full ecology of that stream. And so carrying sediments is an important part of the function. And here's a slide stream function. We know that it transports water and it transports sediments. And the second thing that we know is that the stream is a special ecological environment that provides habitat to different aquatic organisms. Also, it grows a very special ecological system on its banks that provides food for land organisms. These include plants, animals, and vertebrates, all kinds of animals. And because the riparian area grows vegetation that first is special for these banks, it accepts some wetness, some dry land, but also these vegetation usually provide food and regulate temperature of the water in the stream. The stream, in order as it develops, it creates features in its bed that are also important to that ecological function. So we have channels, we have pools, riffles, glides, and runs that provide invertebrates, even fish. They do different function in the different features, and that helps their survival. And so when we're talking about restoration, which is the title of this workshop, we're not only saying that we're going to restore the water flow, which is how a lot of engineers through time a natural design that restores all the function of a stream, from transporting water, sediments, to becoming a habitat for organisms, and have the diversity of biological organisms that should be there in the system. How will we do that? Well, it's first by learning how these streams form, basically, and what are the processes by which stream form. And so thousands of streams all over the world has shown something very important, is that there is a flow that has been defined by river scientists as the channel defining flow. And that's basically the flow that carries the highest amount of sediments in it. And so that flow was calculated, and it was found out that it matches in the stream, in the in nature, the part where the channel looks like a ball-shaped section. And so you can go actually to the field and look at the stream, and it should have a flat area, floodplain, and then it has a ball-shaped part, you know, when you're looking at it as a cross-section. And that one, when you determine it in the field, you go back, it actually matches that, the flow that carries over a long period the highest amount of sediments. So basically, this is, everything can be actually calculated back based on the Bankfull stage. Since you can determine that Bankfull stage from the field, you can always go back to it and try to restore a stream to look in this shape. By the way, that Bankfull stage was found to always carry the 1.2 to 1.5 year flow in it. And so that's the Bankfull stage. In the field, when you go, it's when you look at a point where it could be the incipient point of flooding in the cross section right there. So when the point where one more drop will just flood it into the floodplain, that's your Bankfull. And streams as being very important to carry water and sediments, but it's not just random. As we said, the channel forms in the area that produces a storm pattern, and then that channel forms to carry the 1.2 to 1.5 year storms. It also carries a balanced amount of sediment. So these streams, when they're stable, on a regular day, there's a balance in the amount of sediment carried by the water, and so the flow based on different storms that occurs annually will carry a certain size of sediments. If the typical flow on a daily basis is a certain amount, it's going to carry all the sediments that are small enough to be carried by this. And then when we think about the Bankfull, we calculate that Bankfull flow, these specific sediments that usually are carried by that typical flow. So now when we do any trigger that changes that balance in nature, whether sediment-wise or water-wise, that's when you get instability. So for example, urbanization converts pervious land to impervious land. And since that happens, what will happen is that when pervious land becomes impervious land, you have, and these strong flows will carry larger sediments than typical, and that causes erosion. So in this balance, the water is going to be down. You're going to have the arrow point more, you have erosion on the banks, and you have undercutting in the bed of the stream. On the other hand, if for any reason there's a normal flow, but for some reason sediments were being accumulated, some forest was removed, and it causes a lot of sediments, as a So the flow, a lot of sediments are going to start depositing in areas where they did not before. And this is that sediment part of the balance going. The causing deposition, creation of streams, maybe even converting the channel into. So stability means a climate-based bankfull flow that is consistent, that carries a typical sedimentation, and any messing with that balance will cause instability. So in order to be able to restore a channel, we need to understand how is of the channel when stable. And so we do everything, because the bankfull can be determined in the field for any type of stream, because even a stream that's eroding, you can find actually the bankfull is always trying to reform again. So there's either a notch on the side of the bank, or you can see the whole bankfull reforming with time. So you can always calculate everything and relate it to the existing bankfull. The cross section of a stream at bankfull is called the channel dimension. That's the definition of it. And these streams, they change as you go downstream, as the watershed gets bigger. So you have to be able to understand when you're measuring a channel dimension and trying to measure everything to it, you need to understand that the section you're using, that channel dimension is valid too, because you're going to do all your calculation based on it. There's no specific depth, because again, these streams, or they have features too. So the only thing that we can really relate back to a natural stream is that channel dimension, which is the cross section of a full stream, the bankfull. That's your channel dimension. And so that would be the cross section. So we're looking now at that cross. We looked at the cross section. We have a tape section that will carry the 1.2 to 1.5 stream with floodplain on the edges. What about the top view? If you look at the top view, the stream meanders naturally. Natural streams, historically, we have come back and we straighten them for many reasons: land loss, land use, roads, buildings. But in reality, that meander has a big function. The meander is a way to it starts creating these meanders in order to decrease the slope, right? When you the straight A to B, if there's a 10 feet difference between these two and it's 100 feet distance, that's a 10% slope. But when you go along the meander, that slope drops by half, if not more, and become less than 5%. And so that's what the meander's role is in nature. Now, when you're restoring the stream, you want to think about re-meander. In order to re-meander stream, you have to be able to identify and reconstruct a typical meander in that typical stream. And so the points that we measure, there is your belt width, which is the distance from the bank to bank along the height of the meander. You have the wavelength, which is basically the length, the straight line between point A and B. You have the amplitude, which is from the middle of the stream to the top of the stream. And there's a definition of the curvature itself. You can measure the radius of curvature. There's a very straightforward way to do it in the field. And then you can identify your inflection point. Once you have that, that helps you in being able to actually identify and measure a meander. And if you need to re-meander a stream, you can always use these terms in order to re-meander it.
Dr. Jabber, sorry to interrupt. You're breaking up quite a bit.
Huh.
I'm wondering if maybe you want to try to call your phone and maybe use the audio through your phone, if that might be better.
We can do that. Let's see. Did you have that phone in your?
Yeah, I can pull it up real quick, I think. Let me get to my email.
I think I found it. I actually to put another microphone so I don't have to use my. Can you hear me better now?
You haven't broken up yet, so I think.
Okay, so I put a microphone instead of using the laptop mic. Can you hear me?
Well, I think you just might have cut out for a little bit.
So weak internet. Am I still cutting off? Or should I call the number?
I think try calling the number and see if
Okay.
that works better.
Okay. Can you hear me now?
Yeah, that sounds good.
Okay, very good.
Thank you.
Let me lower my volume here so that it doesn't interfere. Okay, very good. Okay, so with that interruption, that was the break, by the way. Okay, so the third thing we were talking about was the third thing we were talking. So we talked about the cross section. We've talked about the top view that shows the meander. The third thing we're talking about is the shape of the channel itself and the features along the profile of the channel. So we have typically we have pools, we have runs, pools and riffles that go in between. And so from the riffle to the pool, we have a run, and from the glide to the
from the riffle to the pool, we have a run, and from the pool to the riffle, we have a glide. And what these are is, like you can see the cross section of each. Usually riffles are shallow, where water, you can see visibly the water flowing, and you have deposition of large sediments. Usually it looks like they have some rocks in it, while the pool is a deeper section that where when you look at it, it doesn't look really that the water is really moving, and usually so very small sediments deposit in pools as a result. And again, those have a function in how the different organisms can survive, and they have a function also in stability of the channel. So again, when we talk about natural channel restoration, what are we talking about? We're talking about the restoring a channel to meet the full ecological function of the stream. And so we need to figure out what is a bankfull, how can we make sure that the flow and the sediment flow without deposition or erosion. And so basically, the only thing we have from the stream we want to restore is the reference, the bankfull section, because we can determine that from the field. And so what we need to do is figure out how did it look before it got degraded. And the best way to do that is to find similar channels in the area and collect data from these similar channels. And so these streams that are healthy, that are in your area, these are called they're called reference reaches that you use. And so if you're lucky enough to be able to find a healthy stream in your area, then you can compare, scale your stream to that stream using the bankfull as a common term. Now, if the reference reach does not exist, there are things we call regional curves that help you relate your bankfull to different healthy terms like the meander wavelength, that the distance between the pools, etc. And so when you do a restoration project, the goal is that there's no more erosion or accumulation of soil. So that's your ultimate goal. So there's a balance between the water and the sediments moving in the water. The second goal is to make sure that diversity in biological organisms is restored, and so there are habitats for the different type of organisms. And finally, that the stream allows for riparian vegetation to survive and be healthy in the process. So these are our really goals. Our goals are to restore the channel, restore the cross-section, restore the profile, restore the meandering pattern. But before we go and do a full project that involves serious construction work, we need to know where we are in the stream. And so the first step in a process of stream restoration is stream assessment. And the stream assessment, here are the following steps. The first thing you want to know is the drainage area of your reach that you're trying to restore. Where is the water coming from? And then some type of analysis that's going to help you with understanding what are the expected flows in that cross-section based on different rain events. So you would know what the the 1 year event, how much flow it will cause, the 2 year event, the 3 year event, and then specifically you want the bankfull event to make sure that your bankfull that you measure in the field is correct. So you get that watershed drainage area. The second thing is you determine the land use. That's also in the same function, because while trying to determine the runoff at a specific point, you need to know the land use. Is it mostly urban? Therefore, one rainfall event will produce a lot of runoff, or is it mostly forest, so very little runoff, or is it agricultural? So it's in between. So you want the land use and the watershed drainage area. And then you go to the field. It's in red here because that was what we were supposed to do this afternoon. We're not going to do it, but hey, after this workshop, you can all go down to the closest stream and practice by your own. Determine the bankfull is look at the stream and try to find that incipient point of flooding, and so as a result, you can determine where is the bankfull level. After that, you bring your surveying equipment and you survey that cross section, and what that gives you is the channel dimension. So now you know exactly how your channel looks at bankfull and a little bit beyond. You want to measure the floodplain too to understand it. The next thing to do is to actually look at the top view, the pattern. So we're going to look at the sinuosity, which means how the meandering pattern, basically a meander geometry, what's the radius of curvature, what's the belt width, what's the meander wavelength, and then after that, using surveying, you would measure the channel profile and determine how far are the pools from each other, how far are the riffles from each other, what's the shape of the pools, what is the average depth of a pool, what's the average depth of a riffle, what's the average slope of a riffle, what's the average slope of a pool. All these things can be determined from a channel profile measurement. But we want to determine what is that stream made of, because again, remember, the biggest concept that this whole natural channel design work is based on is a balance between sediments and flow. And so determining the type of sediment found in the stream will help us actually understand what type of sediments is the flow typically carrying and what type does it carry in large storm events. And so we do what we call a substrate analysis, and that's also called the pebble count. There's different pebble count that we do, one to classify the stream, to know what type of stream it is, and then we can do a specific one for pools to basically characterize the pools, and we can do one for riffles to characterize a riffle specifically, and we do one averaging the type of sediments all along the stream that we use usually for classification. So once you have, at this point, you have all your data, you want to do your calculations, you can estimate your bankfull discharge and velocity from the cross section at a riffle, from bankfull to bankfull. You have the cross-sectional area, you have the slope, and so you can use an equation like Manning's equation and determine the flow rate that would be at bankfull. You can then go back to your original data where you got your watershed data and where you got your watershed data and where you got your land use, and with a model like RAS, for example, you can determine what the flow that you calculated by hand using Manning's equation at that cross section. What does it refer to? What return period storm is it about? If it's somewhere between 1.2 and 1.5 or in that range, if it's 1 to 1.6, 1.7, then you probably have correctly identified your bankfull. But if you find out that that flow is a 0.2, 0.3 year return period, that probably means that the bankfull you determined in the field was incorrect. So, and that happens. And so you have to go back and try to look at a different location to re-identify a better cross-section. At this point, you also want to assess the condition of the stream riparian zones. And so you walk around, you look at what type of vegetation is there, what's the soil fertility, what is the topography, is it high slopes, is there any concern in urban settings? Are there houses that go all the way to the edge of the bank? Are there locations that are in bad shape? So you do a full assessment of that of that riparian zone, and that will help understand better how a restoration project will be done. And so with that, we're going to look, this is, it's called the Rosgen flow chart, basically, where he defines the different levels of channel characterization that will help you decide what type of intervention, what type of restoration you're going to need to do. So you start with all the data that I talked about earlier to collect your information, and that's called basically level 1. You're able to, from that, you're able to understand a lot of parts of the channel, and these actually, there is a classification system we're going to talk about in the next slide that will classify the stream from A to G. Once you have that, then you start collecting more details at the stream. You calculate something called the entrenchment ratio, which we're going to talk about in a second. Calculate the width to depth ratio at Bankfull, the sinuosity, the channel slope, and the channel material. That helps you add, confirm your letter and add a number to your stream. And so now your classification is anywhere from A to A6 to G to G6 and everything in between. So you have 6 types of channel material, which is what the number defines, and you have letters from A to G that classify your stream. Once you have that classification, you go and do your riparian analysis. Once you have your riparian understanding the full stream, is there erosion? Where is the erosion? And where and what type of conditions is the stream in? Then what you do is decide your final condition of a stream and what level of intervention you need, what type of restoration you need. Is it a full restoration? It's a full project where you're going to completely rebuild the channel and its riparian zone, or is it minimal localized erosion that requires some type of small intervention at the bank, maybe some in-stream structure that will divert the flow to the center. No matter what type of restoration acts you do after level 3, then you have to come back and decide whether what you did is valid and works. And so you have to do some type of assessment. And so whatever was wrong, you want to check if it got fixed. Is it stable? Is there erosion or accumulation of sediments, aggradation? Are the sediments the typical sizes that you calculated that should be in your riffles or your pools? And you can go and look at biological functions. Are you restoring your biological organisms? Do you have a functioning ecological systems? And all these things are the things that are going to determine whether your restoration action has worked or not. So let's go look at level 1 assessment, which is a fast look at the channel and preliminarily determine what letter it is. And we said there's letters from A to G, and these can be determined by looking at the stream. You look at the cross section, you look at how straight or meandering it is, and you look at the slope. And based on these, you can take that sheet with you to the field and you look at it. If it's very high slope, it's probably an A. These are typical natural channel found on the side of slopes, and they're usually confined within the channel. The blue line here is the Bankfull in all the channels in the cross section. The blue is the Bankfull, and the dotted line is the flood-prone area, which is basically double the depth of the Bankfull. And usually the confinement of that flood-prone area within the channel with the bankfull, if the width at bankfull and the width of the flood-prone area are pretty close to each other, that means that this channel is usually highly prone to erosion. These A and A+ are probably in most cases bedrock at this point because they're natural form. We'll talk about a similar channel that is actually not in side of mountains with a lower slope, and these usually are more eroded streams. So B, C, and E are usually channels that are naturally formed that could be stable, or in general, the B is usually a stream that has a slope from 2 to 4%. C and E have slopes lower than 2%. C is usually a wider stream, and again, depend on the area. It could be a natural channel formed like this, or it could be an E channel that changed with time to a C channel due to minor erosion. But these are natural channels. You can see the E is the most stable type of channel, with the channel being very narrow and the flood-prone area being very wide. So we have a very high ratio of flood-prone area to bankfull width, and that's what the entrenchment ratio is. It's that ratio of the flood-prone area to the bankfull width. Even in the sea, usually that entrenchment ratio is pretty high. Now, another type of stream is the braided channel, and these are multi-channel systems. We have a D and a DA. The D can have any slope under 4% usually, and it's completely braided with channel intertouching each other. And then you have the DA where it's braided, and there is small connection, but the main channel are still defined, but they're connected to each other with smaller channels. That usually have a slope of less than 0.5%. The F and the G are forms of eroded C and E channels. The G is usually the next step from C is if it starts eroding. If you look at the cross-section of G, it looks a lot like the cross-section of A, but there isn't a high slope that causes that type of form. So and also the meanders are much less than your E and C. So that is a form of eroding channel that we typically find in urban areas. And then F is your canyon, basically. It's a G stream that kept eroding and going bad, and it becomes basically this typical U-shaped channel that keeps deepening if erosion keeps happening. So that's your level 1. You take that sheet with you, you go to the field. If it is in that shape, then whatever shape it is, you can determine what letter it is, and then you can confirm that by using calculation. So 2 terms that I mentioned already, but let's check what they are exactly. So the entrenchment ratio is, again, the width of the flood-prone area. The flood-prone area is it's the width at double the elevation of the bankfull depth. So you double the bankfull depth that you determine in the field, and you measure the width at that point. That's going to be your flood-prone area, and the bankfull surface is that width. The ratio of these two is called the entrenchment ratio. If that number is low, that means your channel is completely confined and highly prone to erosion in the upper air above the bankfull. While if it's very high, that means your flood-prone area is very wide and the bankfull is very narrow, and as a result, your entrenchment ratio is low. The second term we talked about is sinuosity. We said it's a determination of how much the stream is meandering, and it's basically the stream length. So you measure the distance between A and B along the stream, and the valley length, which is the straight line between point A and B. You measure that distance, you divide the stream length by the valley length, and that gives you how much sinuous, the sinuosity of your stream. We go here to level 2. So that level 2 confirms your letter and adds a number to it. So that's a flow chart again that you start with. The first line is single versus multiple channel. If it's multiple channel, then it's going to be a D or DA, and that's going to be based on your slope mostly decides to what type of stream it is, D or DA. If the single set channels, which are more common in this area, is what you're interested in, you start with your entrenchment ratio. If it's under 1.4, it's going to be an A, G, or F. If it's greater than 2.2, it's going to be an E or a C. And if it's between 1.4 and 2.2, then it's a B. From that point, to differentiate between the different groups within, you look at the width to depth ratio, and that's at Bankfull. If it's below 12, then it's either A or G. If it's higher than 12, that's an F for the first three. For E and C, determining that difference, E has a width to depth ratio smaller than 12, and C has a width to depth ratio greater than 12. To confirm more, you look at the sinuosity. If it's less than 1.2, it's an A, greater than 1.2, it's a G or an F here. With E and C, you have greater than 1.2, it's a C, greater than 1.5, it's definitely an E. Now, as a disclaimer, if you look at the bottom of your screen, you can see that there's certain changes you can do. Basically, entrenchment and sinuosity ratios can vary by plus minus 0.2 units. What does that mean? It means if you measure 1.6, 1.2, I mean 2.4, it can be anything. You know, it doesn't mean necessarily it's a B. If it's 1.4, it doesn't mean it's a B. It could be 1.2 actually. Same thing with velocity. You can see that most of things differentiate at 1.2, but then ratios can vary by plus minus 2 units. So that means if you measure a sinuosity of 1.4, then you're actually stuck into your. Did you lose my screen?
Oh, I think we just lost your screen.
Yes, my internet seems to have restarted again. It's all kind of people checking.
Well, I guess we'll take another quick break while we get your screen back up. Unless you want me to try to do it on mine and just. I know you have the
sure. Little. I won't be able to see it. That's you'll have to tell me what slide here. So we could do it like that. Do you want to do that?
Well, does it look like,
you know, you just tell me what to do.
Does it look like your thing is restarting or?
Let me check here. Yes, it is restarting.
Okay, so we'll just give it a minute.
There's not happening. Like Looks like the internet got lost. It's connected to the Wi-Fi. Just that there's no internet. It's not coming back. I think Spectrum cut me off. Maybe I used too much bandwidth.
Okay, I'm wondering if maybe we.
Yeah, if you can do it, and then I will just say the number of the slide as I'm going, and then we can continue. How about that?
Because do you have like
So
the book with you?
I
can see.
have the presentation in front of me.
Oh, okay.
I don't need that.
Okay, so let me get it back sharing on mine.
Okay, we're on slide 16.
Okay, I have slide 16 up.
Very good. Okay. Sorry for the home teaching problems. So I was talking about how, you know, these help in determining the letter, but again, keep in mind that entrenchment and sinuosity issues and width to depth ratios can vary, and therefore you could fall like several times you would measure 1.5 and we're like, oh, it's definitely a B, even though there's never been a B in that part of the country. And then it's really because the entrenchment may vary between, you know, plus or minus 0.2. So actually 1.5 can easily be AGF, for example. And same thing with 2.1. It could be actually B, E, or C. So that's to keep in mind. The second part is the letter. As you can see at the bottom, determines your channel material. We said that we do a pebble count. Basically, we do a cross-section, collect different type of material in the bottom of the stream. There's a specific method to do it, and we'll talk about it later, that to collect all these material, you determine your D50, which is basically the average size of the particle, the channel material in the Bankfull section. And based on what that D50 is, whether it's bedrock, boulders, cobble, gravel, sand, or silty clay, and there's a very specific measurement to define each of these categories, you can give a number to your stream. So now it's a C. If it's boulder, it's a C1. If it's silt and clay, it's a C6, and all these different groups in between. If you look also based on the slope, there's sub-classification too that divides. So for the C, it can be a CB, C1, CC in general. And what does that classification help with? It helps with selecting the appropriate reference channel to do your measurement, or if you to do your restoration based on. So if you select a stream that has the same classification of your channel, or if you know what your channel used to be before it changed with time, then you can target that for classification. Same thing with regional curves. Sometimes these regional curves are divided by stream classification, and so you can use the classification for your specific stream to take numbers that you would use in restoration. So now we're going to go to slide 17. And so the slide 17 is level 3. If you remember, level 3 is determining the condition of the stream in the riparian zone. And so there's different types of instabilities that happen in a stream. One is a result of large changes at watershed scale. That could include upstream channelization that caused water to go faster, especially if they changed the whole channel and made it concrete. And so the fast water will flow down and cause disruption in all of the downstream section, or large-scale development, a city developing upstream that changed the hydrology. Now the 1.5-year storm is producing 2 or 3 times more flow rate as compared to the typical storm that formed the channel in the beginning. So that's watershed scale instability. Some instabilities are really just at in the reach level. It's resulting from something that happened just above or within the stream reach that you're trying to fix. And these could be a bridge pole being constructed on it, a tree falling that caused a flow change, anything, a constriction of the channel because of a pass put on top of it and a culvert under that pass that was not correctly sized. These can cause erosion at the downstream end and at the upstream end, and these are local instabilities. So there is a channel stability assessment. There's 2 levels. One is where you try to determine what level of deterioration has happened to your stream. We call that channel evolution. It's the different shapes and classes that a stream goes to as it goes through usually a watershed scale instability. And then we have bank erosion assessments, and these could be for both, for all kinds of instability, where you can actually grade your bank and decide if your bank is prone to erosion or not. Slide 18. And so this is a picture showing watershed scale instability. This is a wide canyon looking channel that I took a picture of in Van Zandt County. And you can see that the normal water level is very small, but due to storm, due to urbanization and channelization upstream, large storms causes a very fast rise in water that's causing erosion all the way to the top. The stream has been clearly eroding for years. You can see that the Bankfull stage is probably way below where the root reach, and as a result, it's undercutting the trees and resulting in trees falling into the water. This here, on the other hand, you can see that the stream is not in perfect shape, but you can see there are certain grasses on the lower right. This is slide 19, by the way. Grasses are growing, so even though this channel is not in great shape, there is some erosion happening. You can see it's not a immense instability because soil is staying put enough for some grasses to grow on it. But there is a small nick that is forming in the center, and that's because actually I'm standing on a bridge taking that picture, and you can see that the pole was directing the water directly into the bank, and so that was causing erosion at that section. That can be fixed by just putting some in-stream structure that can divert the water back to the center. Slide 20. This here is in Fort Worth, and this is just across from the stockyards. And you can see that the bridge, there's a bridge that was built there. And if you've ever been involved in any bridge construction, they usually ask you to design it such that it rarely overflows. And so that's probably designed for the 100-year flow at that section. The problem with such a design is that you widen your stream so much at that section that the stream that is supposed to be, you can see how narrow and shallow it is in reality. as it comes in and it faces this concrete wide section that is flat, it's going to actually spread, and all the sediments in it are going to settle. And you can see that there's a lot of sediments that already settled in front of the two right opening or box culverts under the bridge. And the channel has reformed a small channel for itself inside. And so that's a channel widening that caused sedimentation, because the channel is trying to work again to reform that bankfull through it. And so we'll talk about potential solutions to that later. Slide 21. So channel evolution is basically a way to identify how streams changes as they are some kind of trigger that cause instability happen, usually construction and development in the watershed. So we're going to start. This is one typical type of channel evolution. There are other types that that you can see, but that you can find actually in literature. But this is a very typical one and typical of urban areas specifically. So you could, if you have an E channel originally, if your drone creates E channels, you can see that the bankfull is basically the same as the bank height. Whenever the water overflows bankfull, it goes into the floodplain. There's complete connectivity there. The water helps the riparian vegetation to grow, which in turn hold the the bank stable at that section. If construction starts happening, and now for typical flows that fill bankfull, you're getting higher flows, then that flow is going to be fast enough and it's going to start causing erosions in the bank, and the stream starts changing from that rectangular E section. This is in the top, wherever it says E4, into that dotted line. And if you look at the, the plan view, you can see how, even though the meander are still existing, the stream is widening, and therefore that meander will start looking a little bit less sinuous. And so this is going from an E to a C. The C stream, as if it can be stable, there's actually natural seas as we talked about. So your channel evolution could have started in the second figure, but E goes to a C first. If instability is still happening, they're still building downtown, and now the bankfull is producing even more flow, then your bankfull, which is the water level in that picture, is getting more water as a result of increased development, and the extra water is gonna start flowing in the deep end of that C cross section, and it starts undercutting and deepening. And so as it's doing that, that stream will deepen on the deep side, and then it will start settling on the shallow side. And so we're going now from a C to a G stream. And so the G stream is a little bit more straight, even less sinuosity, as you can see from the plan view change from a C to a G. It's narrowing a lot. So it narrowed nearly to as narrow as C is, but the sinuosity has completely changed, and the channel is much more straight. And you can look at that G channel where your bankfull is very confined, and if you double that distance, you can see the flood-prone area width is still within the channel. So now these highly erosive storms are still within the channel, so they're going to start eating at the banks and undercutting under the vegetation, which slowly will start falling in sheets into the water to convert that G channel into a canyon, basically. And so the G will widen again from G to an F. So now you have a very wide channel that is very little sinuous, and it has very straight banks, and your bankfull and flood-prone area are basically the same width. And this type of channel, the F channel, which is the canyon, will keep deepening and widening until no more development is happening. And so at this point, if the channel is, if the watershed is completely constructed and there's a pattern of a typical flow for each storm, including the 1.2 to 1.5 year storm, then the channel will start adapting to the new flows, and it's going to be slowly restoring itself over a long period, and will go back from an F to a C, and then from a C to an E. And then it stabilizes as an E, which is bigger, much bigger channel because it's holding a bigger bankfull flow. And you can see that there's a new floodplain that's forming where the old channel was. And then the old floodplain now become a terrace. It's a former floodplain. And so now you have an E, but it's larger, that accommodates the new flows, and it's stable. What we have seen here, if we go now, as a lot of that evolution is happening in our streams, you can easily notice that a lot of the urban streams are either a G or an F. And so the best thing that can happen to you is to catch a stream in going from a C to a G or from a G to an F. And that's where a restoration will be most economical, as less work needs to be done, and you can catch it at that time, restore it, and try to guarantee it. Now, the key here is that if you're restoring a stream during its evolution and your watershed, though, has not finished being constructed, you need to account for the extra flows that are going to come from future construction. Unfortunately, you can do that in the stream. If you build a stream for the future flows, it's going to be too wide, and it's going to cause sedimentation. And if you build it for the current flows, and then you have future flows that are higher, it's going to erode again. So what's the solution? The solution that when you're doing a costly stream restoration project and catching a stream early enough from C to G, it needs to be accompanied by regulation at city level that will guarantee the construction of green stormwater infrastructure in new building, such that the runoff from any new construction after the restoration has been done is equal or equivalent to the runoff of pre-construction. That is really your solution at that point. This is again a little bit more details on the channel evolution, that how that erosion happened, why does deepening, widening happen, and where do eroded material accumulate. This is slide 22. Slide 23, degradation and widening. Basically, this is a channel that is probably a C channel that's becoming a G channel, and then you can see that you have erosion as a result. This is partially because of the flow, but it's also partially due to the mowing of the grass. The riparian vegetation protects your banks and allow higher flows to have very little impact on your bank erosion. But when you have it completely mowed and you have higher flows due to urbanization, you start seeing erosion like this. And so here's your C to G, and this is your G to F at this point. You're losing sections of your bank at a fast rate, that it's sliding probably in sheets and causing erosion. And so this is a G channel that is becoming an F right here. With, you can even see it got to bedrock and in some sections, which is lucky for them. Otherwise, this thing can keep widening and deepening until the part falls in it right there. This is your F channel. Again, it's the same one in the Van Zandt County, and you can see it's widening. It's very wide, very deep. You can see that this wastewater pipe, which probably was either at right on top of the water, or because it doesn't have concrete around it, I suspect it was buried when installed first. It's completely bare, and it's way above where the bed of the stream is. You can see the channel is becoming braided inside, but then again, every time a storm happens, the water goes all the way to the top and then goes down and erodes underneath the trees, and these trees were falling at a very fast rate. So if you look at a bank, how can you make sure that it has low erodibility? Well, there is a way to do this. So now we're slide 26. There's a factor called Bank Erodibility Hazard Index. It actually is a sheet with numbers. This is a graphic explanation of it. And so when you look at your bank, does it have high or low erosion potential or medium erosion potential? There's several factors you want to look at. One is the bank height versus the bankfull depth. That's basically your entrenchment ratio. If you if the bank height and the bankfull are the same, then you're actually in great shape, because these flows, these bankfull flows, are not very erodible, and the high flows have space to dissipate above the bankfull. If it's a little bit below the bank, then you have medium erosion potential. So the bankfull, when it overflow bankfull, there's still some bank, so it's going to cause some erosion in this section. If it's way below the bank, then it's a high rate for high possibility for erosion. The bank angle also, a gentle bank angle has low erodibility potential, while steeper or even negative angles have very high erodibility potential. The density of the root and the bank surface cover. So how much vegetation and the type of vegetation with very deep-rooted plants are on your bank. If they are there and your root go all the way to the bankfull level, then you're in very good shape. If the roots go barely a little bit above the bankfull level, then that's a little bit worse. And again, if they're much higher, that's very bad, because you're going to have undercutting underneath. That's going to cause that bank to start falling in sheets. With the cover on top, this is here a root wad shown in the top picture, but then also the cover. The cover on top could be vegetation existing, or it could be large tree debris that deposited from a very large storm and sat there and get established there. Any deposit, any cover of your the surface of your bank is considered protection that would reduce the erosion potential. Soil stratification is also an issue. If you have a homogeneous soil in your bank, then you're in good shape, because there's good cohesion between same type material. If it's a little bit stratified, like 2 or 3 types, then you have a higher erosion potential. And if it's highly stratified, then there's high erosion potential. And finally, the particle size. Small particle size like clay are more erodible than gravel, which is more erodible than boulders and and bedrock as a result. Again, there's a number sheet you can get online. Just Google BEHI, B-E-H-I, and it will give you a score of 50, with the higher score being higher erodibility. Sometimes it's not very obvious why there's erodibility. You can see that in this picture, they used some erosion control material and they planted above it, and they were wondering why it wasn't working. And it was actually working all along that stream. That section specifically was having problems, and the reason why actually was that it was way more shaded than the rest, and as a result, it had problem establishing the vegetation. So there's other things when you're evaluating your riparian area that you need to check on beyond just the bank erodibility factor that could cause problems. With that, we're going to talk about how to restore our streams, and there are several options you might have depending on your location and the constriction and restrictions you have in your area. So the first option that is usually recommended is, if you have a wide area and an ability to do whatever you want, is basically to design your typical stream channel and know the exact dimension that you need for a bankfull, and you know the exact meandering dimension you want to take, and then rebuild a stream where the bankfull is equal to the existing floodplain elevation. You build it on the side, and then your old channel, which it was, you know, dotted in red right here in the picture, you can refill it and make it maybe a wetland and a pond where water would overflow if you have to control flooding in that case. But you would have the ability to reconstruct the channel from scratch. So this is again slide 29 now. This is a typical example of how a channel is completely constructed from scratch. You can see how symmetrical it is. The bankfull was calculated, the channel was built, and the meander was designed. And so that shows you that streams can be built to be stable from scratch, basically. This is a top view of a system where they used priority 1. You can see the stream that looks perfectly like a sine graph. That's clearly man-made, and so, but it wasn't where the channel used to be. You can see to the left, that's where the channel used to be, and it was eroding, it was endangering that road, and so they had space because this is a park, and they were able to recreate a stream, and then on both sides of that stream, they can create, this is during construction, they can put a wetland or a detention pond that can, if for some reason that stream overflows, it can overflow in those rather than flooding the road, or I think there's a golf course on that side. Your second priority is when you're limited, you don't have a lot of space. So this is slide 31. You don't have a lot of space and you're confined within where the existing channel is. And so in that case, what you do is you build your bankfull at the bottom of that floodplain and create a floodplain within the meander wavelength that you have for your channel. So you create your new bankfull, so that reduces, and then you have a floodplain to dissipate the flow, and then the old floodplain you recreate as a terrace in that case, and then you remeander it. And here's a example of this. You can see this channel was it's a G channel probably. It's high edges with water at the bottom of it. They came back and then they recreated a channel. They remeandered it, created a small floodplain for it, and the old floodplain became a terrace in this process. Slide 33. Your third priority is when you're completely confined. You have very little space to create a big floodplain on the edges because you have roads, you have buildings that are built all the way to the edge of the channel. And in this case, again, knowing that your bankfull is going to be much smaller than the existing channel width and depth, you can always go back wherever the channel is. Now, there's usually very little meandering possible in this case. So there might be requirements after you do calculations to do some typical reinforcements like or put in-stream structures to reduce it. But your bankfull is still less wide than the existing channel. So you rebuild the channel to have a bankfull, and that gives you enough space on the edges to create at least one row of trees or deep-rooted vegetation layer. And so that's what you do. You put a little bit, one row of riparian vegetation on the edges, and then you slope the stream back to wherever you're allowed to. And if that slope is too steep because of your limitation, then you can do a structural stabilization on that top channel. But on the bankfull and the floodplain, no stabilization is needed at that point. And so here's an example, slide 34. The picture on the left is how the stream looked like. It looks a little bit like it's becoming an F. It's It looks like a U. It has steep edges. On the left, they had private land that they did not have permission to change. And on the right, I think it was a national forest. This is in North Carolina. And then you can see there's actually mountains coming all the way to the edge of the channel. So they had very little ability to move beyond the existing channel. And so what they did is they calculated the bankfull, recreated the bankfull channel, and that gave them a small layer to use as a floodplain. And then they used some type of riparian vegetation from this area that they planted, and you can see now there's a 2-level vegetation. We can't see the floodplain because it's completely covered with vegetation, but it actually stabilized that channel by allowing just 1 layer of vegetation on each side. Slide 35. So to get back to regional curve. So as I mentioned, is when you're doing your design, I'm going to stress that point again. All you do is figure out the bankfull at your eroded channel, your project channel, find a reference reach, measure the bankfull and everything else in that reference reach, and then you can scale all these other features to your actual stream based on the difference in bankfull between the two. Now, if you don't have a reference reach, you can look at a regional curve, and these are examples of regional curves. So the first graph on the top left graph, it's the belt width as a function of bankfull width, and you can see that let your bankfull width, let's say your project bankfull width is 20, and you can all go straight into that graph and look at the middle line, and you can look at your y-axis, and it tells you if your bankfull width is 20, you probably need to use a belt width of around 70 or 60. So same thing with radius of curvature as a function of bankfull width, meander wavelength as a function of bankfull width, pool-to-pool spacing as a function of bankfull width, maximum pool depth as a function of riffle mean bankfull depth, and maximum riffle depth as a function of mean bankfull depth. And you can see that we're relating those different things back to the bankfull, because the bankfull is measurable at the eroded site, and that's basically the way. Now, these are regional curves, so you can't use the North Carolina curve to design your stream here. Each region should have regional curves, so these are starting to develop in Texas. Each area is producing some. Harris County produced some for the Houston area. I think the San Antonio River Authority produced some for the San Antonio area. Here in the Dallas area, we don't have some yet, but there's someone who did a study in southern Oklahoma that we can use some of their data. So there is potential for those. And if you ever get involved in stream surveying, always keep in mind developing regional curve for your area. Slide 36. So in many cases, especially in urban places where we are always faced with priority 3. And so what can we do really is we need to stabilize the stream by using some type of structure. Unfortunately, historically, all these in-stream structures disturb the stability as well as the biological function of the stream, whether within the reach they fixed it or downstream or upstream. If they channelize it or if they put gabions, all that usually does not meet the requirement to make the stream functional completely. So we need to think about structures that would actually be in line with our natural channel design approach. And so we'll talk about that in a second. This is the site in Van Zandt County that I was talking about, where this is a tributary to that main stream. And the problem with that area, that the flow was being so high from the construction in upstream from that area, from the Dallas area, that whenever it flooded, water went back into the tributaries, and as it receded, it eroded these tributaries. So that guy was losing land close to his house and where his cattle grazed commonly. So his solution was to dump everything he owned into that tributary, but that is not a valid method. So here are some of the valid methods we're going to talk about. The first one is a root wad. Basically, that's a tree that that was probably removed. If you find a tree remover in your area, you take the root ball of a tree and a certain distance, probably 3 to 4 or 5 feet, depending on the thickness of the tree, and then you can insert that root wad in the section where that has erosion. What happens is water comes in and the roots, usually that tree is put, a third of it should be below bankfull. So whenever the flow rises above bankfull, it's basically using the whole tree, which causes all this roughness that diverts the water back toward the center of the stream and stabilizes the water right after the root wad, which can cause that part to collect sediments. You know, sediments will settle in it, and it would refill your erosion section by itself. Another practice is J-hook veins, and basically these are rock or log structures that have specific design. There's a specific angle going down. There's a specific height at which the top of the vein should be at, and it's directed toward the flow. And so in the picture, the flow is coming toward us, and in the drawing, the flow is going from right to left. And so the hook makes the water, the vein, I mean, the arm of the vein makes the water go straight into the center of the stream, and the J part of the hook, which are all below bankfull at this point, they actually prevent water from creating eddies that can cause problems on the other bank and force the water to stay in the center. Slide 40. This is a cross vein, and basically it's two veins connected in the middle, and you can see that they're building rocks that are going toward the flow. This is when you're having erosion on both sides, and the cross vein can force the water to go to the center of the stream. The other thing it does is it can be used as a drop structure. If you don't have space to do meandering, you can build a cross vein and then restart the bed of your stream on the downstream end at a lower elevation, so that you can control slope upstream and downstream. That can be effectively used when your design says you should do a meander, but you have a construction that doesn't allow you to put a meander. So you can put a cross vein that can double as a drop structure to control the slope. This is a cross vein seen from downstream looking upstream, and you can see that there's two arms of the cross vein, and this is water was nearly at bankfull at that picture, and you can see that the rocks in the middle are completely submerged, so they're all below a bankfull, but you can see that they're still causing water to infiltrate, and you can see that it's diverting that water toward the center of the stream. If your stream is very wide, you can use something called a W-weir, and that's basically two cross veins connected that slope down and then up again and then down. So so that way you don't, if the stream is too wide, forcing all the water to go into one lane can cause serious cutting of the stream bed. And so what you do is you divert the water into two or more pathways, so you have less problems. This is just for very wide stream. We talked about building bridges that have culverts for the 100-year flow. So this is slide 43, and what we have is actually a design here that shows where you can actually design the culvert to be at different elevations such that the flow rate under the bridge is designed to be equivalent to the flow upstream of the channel at any depth. So you can play with the height of the culvert and the size of the different culverts and do a calculation of flow that will show you that at each depth, the flow going under the bridge is equivalent to the flow in the stream. And here's an example of that in the picture. Slide 44, we're going to talk about vegetation now. All these calculations usually assume that vegetation is going to be restored. When you do a restoration project, you need to make sure that riparian vegetation is restored. And so in assessing your stream, the reach you want to do control on, you can see that you need to see what type of vegetation is there, what type of plants can you remove, which one you need to keep, which one can you remove and replant, which one cannot be replanted. Are there any specific trees that needs to be protected, even though in your design the stream goes right in the middle of them? Maybe you'll need to adjust your design accordingly. And you can collect ecological data too at that site. Then you do a plant inventory. You get some specialists that understand plants, riparian plants specifically. You know, TWDB is a good resource. Your Texas A&M Forest Service is a good source. And the plant professionals, nurseries can help also. And you can have a full inventory of the existing streams, which ones are natives, which ones are adapted, which ones are invasives. And once you have that list, then first it helps you develop your riparian vegetation list, and two, it helps you decide which trees, which vegetation to keep, which vegetation to remove during the project. The soil fertility is important. In some cases, if a stream has been mowed and grazed for years, there's a chance it might be low on some of the nutrients, depending on the area. It's good to know your soil fertility. You can send the soil sample to the A&M Soil and Crop Science labs. There are other labs that do soil fertility testing also. And based on that, you can decide whether you want to include plant-based compost or mulch in your planting process, or whether the soil is actually it's fertile enough to support the riparian vegetation that you're going to bring to the site. Slide 47, again, invasives are a problem. You can identify the invasives from when you had your inventory, or if you're doing a small project, you can go to this website here listed that will tell you a database of invasive plants. Now, some invasives, the more removing invasive and replacing them is very good, but if you have invasives that are full-grown trees and you don't have a good plan to stabilize the section when you remove this tree, it might make sense to keep that tree sometimes. Sometimes you might make a decision that even though this specific tree is invasive, it's more disturbing to remove it than to leave it. But if you have grasses, small plants that are preventing or could prevent your riparian vegetation from growing, or could endanger because they don't have deep roots, they can be a problem for the bank. These needs to be removed prior to the project. How do you put the vegetation? There's different ways. You can salvage on-site vegetation and check with a plant specialist if that vegetation can be transplanted easily, and the cost can be a factor there that you need to account for. The second method is life staking, meaning taking small cuttings from existing trees and plant. You can take those during the winter when the trees are dormant, and then you can plant them in the early springs, and then they can grow and become vegetation themselves from on-site issues. You can buy nursery plant and do bare root planting, which is recommended, where you plant the plant directly in the native soil, the existing soil, without additional soil. And if there's fertility problems, you can always do container plant material. Once you have enough vegetation to stabilize the bank, you can go and seed. You can buy seed mixes that are specifically made for riparian zones that are sold from seed companies. And and you can seed the whole riparian zone, and then that will help with time to establish an even stronger riparian section. Mowing stream banks is not recommended. You know, it's very common in many parks and many locations, but mowing stream banks, in addition to the obvious impact on the erosion of the stream, it's also a water quality issue, because healthy vegetation on the banks can capture a lot of the sediments that are one of the main causes of stream pollutions. Healthy, big growing vegetation absorbs water in small depression much faster, thus reducing the danger of mosquitoes. It restores wildlife habitat in many cases and brings nice and fun animals to your area. And so in general, not recommended to mow all the way to the stream bank. Finally, evaluation and monitoring. We talked about this is level 4 here. Once you finish a project, you know that this is a natural project. There's so many things that can go wrong. So you need to make sure that you monitor it for at least a while after the project, a couple of years, if not more. And what you want to look at, the morphology. Is it eroding? Is it stable in different places? If it's small erosion that's happening, you can always come and do some kind of fixing or put one of those in-stream structures. This is easily done by photo documentation, by putting a camera that takes 1 or 2 pictures a day. And so you can look at that rather than try to use your memory when you go. It's like, was that there before or not? I can't remember. You want to monitor the vegetation, especially the one that you've planted. Is it surviving? Is it growing? Is it holding the bank in place? Is the bank still stable? Is there any sign of erosion on the bank? The shading and temperature of the stream is a way to monitor a reduction in the temperature of an eroded stream after restoration is usually an indication of improved habitat conditions. And finally, the ultimate proof is by collecting regular fish and invertebrate data. You can assess whether your project has increased diversity, increased the survivability of different fish and invertebrate in your stream, meaning that it actually has restored its full ecological function. These are links and resources. You'll have probably you have that printed somewhere and you can use it. And this is my information. This is slide 51 and 52.
Okay, so if we have
And with
any
that,
questions, hold on, I think. So I see one question. So it says, for the larger scale stream restoration methods, how do teams have access to substantial sections of streams for a long enough duration not to worry about flooding during construction? For example, the sine curve that was entirely man-made, photo from the presentation, or the photo of the machines actually in the stream bed constructing the J-hook.
so how do we prevent flooding during construction? Is that basically the question?
Just for that period of time, that long period of time that we have to work to fix
and
it.
so there are strong, well-established practices for work in stream, which is really very similar to what they do right now when they're building gradients or channel, putting concrete in a stream. You know, you divert usually your stream in small sections. Every section you work on, instead of diverting the whole, you can divert a small section around the construction site. You need to take all the necessary precautions to prevent erosion, soil going in, sediments going back into the stream by putting all the required SW3P stuff. And then section by section, you will have to do that. That's the solution. If you don't have that ability to divert the water around, they use, sometimes they pump the water around that section. But these are established construction practices that most contracting companies that do that work know what to do exactly. And there are existing, if we can look up existing stormwater management plan, construction stormwater management plan for a site that will tell you how to do it.
Thank you. Are there any other questions? I will say while we wait for, if anyone has one that they're writing, we will make these PowerPoint presentations. I know y'all don't have a physical book in front of you with the presentation, so we will PDF them and make them available on our website and send you the link so you can reference those links or any of the slides that we talked about. Okay, I don't see anything else. So Nathan, if you're ready, we'll switch over to your presentation and talk about photo monitoring.
Yeah, no problem. Give me 1 second as I adjust. Let me share my screen here. And did that work? I believe it worked.
Yeah, we can see it.
Okay, awesome. So I just want to take a second and say good morning, everyone. And my name is Nathan Glavy. I am an extension program specialist with the Texas Water Resources Institute. And I just want to thank you for joining us this morning and being so cooperative as we are doing this whole new online training due of everything going on. But we appreciate your time this morning. To continue forward with our morning lecture, I am going to cover different management strategies that you can use to help with your stream restoration, your creek areas, just to make sure we're getting that healthy, functional riparian area that we want. And also covering this method of photo monitoring and how that can be used with your projects. So with that, let's get started. So we spent a good chunk of the morning really looking at what exactly are the benefits a healthy functional riparian area bring to our creek system. So I'm about to cover a list of some of the common practices that can be some hindrances that can prevent a riparian area from fixing itself or maintaining that healthy functional status that we want. So the first bullet point would be farming too close to the bank. Mowing, spraying close to the creek. Manicure landscape next to the creek. As Dr. Driver just mentioned, we don't really want to mow all the way up to the stream bank because we're taking away that bank stability with the vegetation. We're negatively impacting the water quality, and we're actually promoting more of a mosquito habitat. So therefore, even though it may look aesthetically pleasing, we're actually doing more harm than good. Chronic grazing concentrations in creek areas. Excessive deer, exotics, or hogs in your creek area. Burning and riparian area. I just want to take a second and note this is relating to those wildfires that can be a huge hindrance to the riparian areas, such as the previous wildfires that impacted Bastrop, Texas back in the day. Controlled burning is actually a good benefit to your creek area and your system as a whole to cycle those nutrients and promote new growth. So this is directly relating to those state wildfires. Removal of large dead wood can also be another hindrance. Artificial manipulation of banks or sediment. So even though we're improving those access points, we're destroying that riparian floodplain area functions that are necessary to maintain the healthiness of a stream. Excessive vehicle traffic in the creek area. Poorly designed road crossings or bridges. Excessive recreational foot traffic. So I want you to take a look at this photo and just look how compacted the soil is. There's really no vegetation growing to protect the banks, and provide the needed functions for a healthy system. This creek is actually Plum Creek, as it flows through part of Kyle, Texas, that is surrounded by neighborhoods and a first to be golf course and everything that holds a lot of local tournaments. So there's just a lot of recreational foot traffic along this creek area, so it's become a very degraded system. And lastly, the last one would be excess alluvial pumping or other withdrawals to your area. So let's talk about some visual indicators of stream health. The above website link is a PDF attachment that will give you more detailed information about these visual indicators that I am about to cover. So just really quickly running through these. Some visual indicators that could be for stream health could include the channel condition itself. And if you observe any sort of down cutting or degrading observed on your channel, or if there's increased sediment loading in your area that's leading to a widening or shallow of your stream. Access to floodplain or any hydrologic alteration that you observe. Is there anything in particular that is impacting the natural flow of the stream with increased pumping or improper bridge crossings that were developed? You want to take a look at your riparian zone and really look at what exactly vegetation is found within the riparian zone and if there's any invasive species there. You really want to take a second to look at the bank stability and look to see if there's any erosion being observed or down cutting on the banks, and if leading to no sort of vegetation protection to help stabilize those banks. The water appearance is another key visual indicator. You kind of want to have that clear color instead of this brown color observed in this photo. Another key one would be nutrient enrichment. So this could be for if you see a lot more of a green color, that could be increase in algal blooms being observed, and that could ultimately always lead to a smell of an ammonia, rotten egg smell that can lead to a issue that something is going on. Barriers to fish movement. And lastly, the last there would be those in-stream fish covers, pools, and invertebrate habitats in your creek area. So other factors that could be applicable to your stream site for those visual indicators can include that canopy cover, observing the trees that are regulating, helping regulate the temperature of your stream site by providing that shade that the creeks need. Manure present in your creek system can indicate that the presence of livestock or excess animals, wildlife being closely related, closely next to your stream or adjacent to it. Salinity, this is not related to natural weathering events. This is more regards to animal manure or excess irrigation from nearby land. A high salinity can lead to bleaching, wilting, or even leaf burn of that vegetation, and can ultimately disrupt the water infiltration rate in your system. Riffle embeddedness is defined as the observed amount of silt and sand sediment overlying and surrounding the larger gravel and cobble-sized particles found in your stream. And this helps, riffle embeddedness is a key aspect that help promote fish spawning and have a fish serve as a fish habitat as well. Lastly, the two other things are macroinvertebrates observed and fish species observed. Macroinvertebrates is a technical name for those aquatic insects, which can be a great health indicator of your stream based on what species are found. And you can easily just look at this observation by kicking around the rocks found in your stream area and just looking to see if there's any macroinvertebrates observed in your area. So let's talk about different management practices and strategies that you can use. So in general, we are called to be land and water stewards. When we're looking at assessing our system as a whole, the impacts of stream flow and water quality are cumulative as the water moves down the system. This means that any sort of management strategy that you choose to implement in your creek area can lead to positive or negative impacts downstream. Like what I like to do is not really looking at the symptoms of your creek area. You really want to look at what exactly is the cause of all the issues that are occurring in your system, if any. So you want to look really, as you're assessing your system as a whole, you really want to emphasize what exactly is hindering it. Has Has something caused a change in the color? Why has there been increased sediment in the area? Or what if I'm missing some vegetation? What could be done to really fix that cause and not just treat the symptoms? So whatever you decide, whatever management activity you choose, should do one or two things. Should either protect the health of an already healthy existing riparian area, or two, if you have a degraded system, whatever strategy you choose to implement should be able to give that degraded system the opportunity to be the healthy functional area. Lastly, another key management strategy you want to choose to look at is the access to your streams. This should be a primary goal along your whole system as a whole, because this will in turn will help eliminate most of the bank erosion caused by human traffic or wildlife interaction with your creek area. This can be done by developing some sort of access ramps or trails with a hardened surface such as coarse gravel or geotextile. This will in turn will help reduce the amount of vehicle, boat, foot traffic along the banks by providing one main access point for recreators. Now on the flip side, you also want to locate the the shade, salt, winter feeding sites, and any sort of manure presence in your area, in your creek system, if any, and locate that livestock you have on your property away from your system to help reduce the time they actually interact with your area. Another key practice you really want to look at into is your management of invasive species. So these noxious invasive species include any sort of species that has a serious potential to cause economical or ecological harm to agriculture, native plants, the ecology, and your waterways in your local area. These invasives can all be ultimately affecting the aquatic, riparian, and upland areas throughout your system and even in the state of Texas. The state of Texas, the Department of Agriculture, currently has a list of about 30 noxious weeds very prominent in the state. Those include some key examples are giant Flavinia, giant cane, and Chinese challis tree are some of the most potent invaders. So if you have any sort of invader, you want to take appropriate action to mitigate these issues. I see that there is a chat really quick. Give me a second if I can access it.
Oh, Nathan, it's just the forms, the presentations, the online link where you can access the presentations.
Okay, no, that's fine. I just got like notified, like a orange lit light right up. So I just wanted to make sure I wasn't missing anything. So, okay, let's go back to it. So going back more on the flip side of these with not talking about vegetation, let's talk about wildlife now. Feral hogs are some of those noxious species that are very prominent in the state of Texas. It was estimated about a 2015-2016 estimate that $52 million in damage was done annually in the state of Texas by feral hogs, and their numbers are just increasing drastically. So these management to reduce invasive species is crucial, along with what we just talked about with limiting those access points and just being called to be general land and water stewards. There we go. So let's talk about more of an example about a best management practice for a degraded creek area. So the city of Austin has this Austin Grow Zone idea, was established to manage for healthy creek systems. And this is more of an example of a passive restoration approach. So the idea of the Grow Zone was taking a degraded system and locating a 25-foot buffer on both sides of the bank to allow for this passive natural plant growth for the entire 25-foot buffer area. They would monitor for changes over time and apply adaptive management approaches when necessary. And so these adaptive management approaches included things such as coordinating periodic trash removals, weed or invasive vegetation management, and native seeding and planting when necessary. The city put a lot of effort into the education and working with local community as why is this so important to the citizens, and if there's any cause for concern, just please let the city know. A lot of citizens, they were getting a lot of calls about the very brushiness that was appearing in the area, and causing of concern for public health safety, such as, what wildlife is present, such as snakes, animals, insects, and just general safety concerns. So the establishment of these educational demarcation signages, which is on the right of this slide, just really emphasize what exactly this project is and what benefits it's actually bringing. So the pictures below describe just an example of an Austin grow zone approach with this passive restoration management. And as we see, as the years go by until the 5 to 10 year program, just because this buffer zone was implemented and only adaptive management measures were implemented in this 25-foot buffer, we see this once degraded system getting its chance and maintaining its healthy functional riparian area that we want. So let's talk about photo monitoring now. The idea of photo monitoring is taking repeated photographs at a set location that will allow you to better assess not only the current conditions of your system, but the changes over time. What's also crucial about photo monitoring is the location selection. You want to make sure you're selecting critical sites along the stream where the force of moving water has potential for detrimental impacts. So this can be done at almost 2 different locations per se, a tributary or high runoff location, or where the stream changes course at a point bar or bend. Whatever site you do choose in terms of your location, you want to make sure you can easily access it over and over again and is a representative of the system as a whole. We're going to touch more on photo monitoring more into details later, but I want to cover 2 different photo monitoring examples from our project partners and even one photo monitoring project that TWDB did. So this is a series of photos that I'm just going to quickly flip through really quick before I start talking again. So these 9 photos are a photo monitoring project that was done by one of our project partners, Sky Louie, on her private property in the Nueces River. So back in the day, the Nueces River had a ATV vehicle problem where there was a lot of interaction with those ATV vehicles up and down the rivers that was drastically degrading the system as a whole, and it was really hindering the chance of the river to naturally recover. A state law was passed to no longer allow driving of ATV vehicles across the state. So that was one practice implemented during this photo monitoring project with the elimination of that ATV motor traffic. At the same time, Sky took it one step further and removed her cattle from grazing along the creek area in the land in the near, excuse me, let me rephrase that. Sky took her livestock and relocate them away from the stream side to help eliminate their interaction with the stream system as a whole. So as we see in the 2007, we see the first photo. It's a very degraded system with very little riparian vegetation, a very wide cobble bed, shallow waters, and with no shade to really regulate that temperature. And as we see, as the years go by within these 5 years, you can see over time, the vegetation starts to grow back up again, the channel starts to narrow, and we have those deeper pools that we are wanting in our system. And that vegetation that's being developed is helping stabilize that bank and providing all that shade that we need to help regulate that temperature. And the habitats that are forming in the stream are helping really slow down that water to help regulate the energy flow across the system and help develop that natural flow regime that we want. So lastly, this next project just really shows, these next photos show the beginning and almost the end of the project within a 7-year difference. We see this once degraded system being able to get this opportunity to be this healthy functional area that we desired. And with this photo monitoring effort to document the changes over time and the current conditions, we see that the practices Sky took to A, the elimination of the ATV motorized traffic, and B, relocating the livestock away from the creek area so they wouldn't interact with the stream system. We see the system being able to get to this healthy functional status that we want. So What's also cool about photo monitoring is that you may be able to get the chance to document high weather, extreme weather events. So again, this is the same site during the Memorial Day flood in 2015. And as you can see by the photos, you see how high the water is and just the overall power of it and how it's just pummeling over the smaller vegetation along the creek area. And at first it's just like, oh gosh, all the harm ecologically and even the harm economically that could possibly come from this. But within the 5 months from May to October, we see the creek being able to basically go back to its original status. Yes, we see the smaller vegetation being knocked out that was once previous there, but we see the creek system as a whole being able to maintain its current status and just go back to its natural flow regime. The water that overleached into the bank nearby, that overleached into the banks into the nearby lands, was then soaked up into the floodplain area that could be used later to help maintain the base flow of the stream during periods of drought or little to no rainfall, and was able to really maintain the status. So if we were comparing it to the 2007 photo, as this Memorial Day flow was occurred back in 2007, there'd be a lot more ecological and economical harm to Sky's property. So let's cover one more photo monitoring example. So the Texas A&M Gardens and Greenways White Creek Stabilization Project was recently constructed within the last 2 or 3 years on a tributary in White Creek. And this would be an example of a natural channel design restoration approach to help really lift and stabilize this degraded tributary that runs throughout the A&M campus. Let's go to this next photo so I can show you a quick little example of it. So this tributary is very degraded, was once very degraded, and was surrounded by a lot of impervious surfaces around the A&M campus. There was a lot of big buildings there, lots of parking lots, really no chance for, during these stormwater events, the water would just get rushed into this tributary, and the tributary itself would not be able to withstand the force of moving water during that time. So if we go into the next slide, I can go into more detail about this project. So during this White Creek restoration project, it was critical for 2 things. A&M's are promoting a lot more outdoor learning now with brand new teaching gardens. And if you look at the creek itself and you look below the creek, just below the L-shaped building or above the L-shaped building, that area between the L-shaped building and the creek south is where this new teaching garden is at the moment. Just because A&M really wanted to promote a lot more outdoor learning on the A&M campus. And all around the creek itself, it's a brand new student living community center at the White Creek Restoration Concept site. The School of Public Health is there. Mays Business School is there to the east of it, and south is the College of Agriculture and Life Science. So a lot of interaction with the local environment was occurring to this. A&M really wanted to take steps to help really take this tributary and lift it to this more healthy functional status that we want. So 3 things were done in particular. They really wanted to include the installation of pedestrian bridges along this site so students or faculty or anyone could go back and forth as they please and not really interact with the creek itself. And those pedestrian bridges are those yellow-orange rectangles found on this map at the moment. They really wanted to emphasize and reshape the 90-degree curve found on this creek. And that curve is found, if you look to the left of the screen, there's that sharp turn on the blue line. That's the 90-degree bend. They really wanted to try to stabilize to help during the times of high flow water as stormwater events, as water gets rushed into there. And they really wanted to emphasize riparian vegetation along this creek area. So a lot of riparian vegetation was established into this creek area into this tributary, to not only help serve as a buffer, but also help further stabilize those banks to help reduce the impacts of erosion and sediment loading into the creek area. And that's just more of a detailed photo of this project. So let's cover more about look into actual photo monitoring approach of this project. So we began this effort in February 2015, and by the end of the project, November 15th, the project was basically completed. A lot of construction occurs on A&M's campus, but we like to say it gets done very quickly. So this first photograph is the site looking just south of that 90-degree bend I was talking about, but looking north towards it. So as you can see, it was lifted and stabilized, vegetation was planted to give it this fighting chance to be this healthy, functional riparian area that we want for our systems. And if we look at the bottom right photo from December 13th, 2017, we still see that this once degraded tributary being this healthy, functional riparian area that we want, and the overall benefit it will bring to the water quality and the wildlife and vegetation that call it home. And this other example is just another example looking from the point bend, the 90-degree point bend I've been talking about, looking east from it. So just to give you a different approach of what exactly was done at that 90-degree point bend turn to help really stabilize it with the vegetation, and just to really emphasize that particular point of the stream, because it was very prone to a lot more erosion than other parts of the stream itself. So let's switch to the last few slides. This idea of, let's touch back up on photo monitoring. So when you're looking at your photo monitoring approach, and when you're looking to implement one, you really want to make sure whatever site you choose, 4 photographs should be taken at each observation site. So you want to do this upstream, showing the nearest bank, stream channel, 2, perpendicular to the streams of the opposite bank, 3, perpendicular to the stream away on the bank where your observer is standing, or 4, downstream showing the channel and both banks if possible. So what I like to say is that you want to look at it as a compass. You want to go north, east, south, and west at each observation site. In terms of identifying each site you take, you can do this by a felt pen or a yellow pad and make a sign to include in the photo. So you can include some sort of identification with the stream name, the site, concerning the specific thing you're taking, and the date. Nowadays, we have a lot more advanced technology where it's able to actually pinpoint with GPS coordinates where exactly you're taking the photo, the actual date, and the time. So if you have that technology, great, please use it. If not, you can go and resort to these more of these old school ways of I'm trying to think of the word, identifying whatever site you're taking, but whatever you choose, you just want to make sure you're able to document properly. Lastly, key locations to monitor, just to touch up on again. Each location should be marked permanently for future evaluations using some sort of steel stake or on the ground reference plus GPS coordinates if possible. So whatever you choose to decide, if you choose like a more of a physical object, you want to make sure whatever object you choose will not move during like a high weather event, during a severe flood, and a GPS coordinates can help solidify that position you can go to, so you can make sure you're able to go back to the site over and over again. Second point, locate the permanent reference point at a safe distance inland, because you want to make sure you're able to go to that site over and over again and not putting yourself in harm's way. Lastly, what's also very critical is that you want to be able to make some sort of map of the stream showing location of each permanent marker and the monitoring point. This has also become very critical for our particular project at the Seguin Outdoor Learning Center, just because we have GPS coordinates, we've had personnel transition, but when we initially made this map, we're able to give it to anyone who can have the capability to take the photos, can reference this map that we created and go back to the same points over and over again and take the similar photos. So we're able to document the same photo at the same location throughout the course of our project. So with that, I am finished. I will leave my contact information up here for a few seconds for those who want it, and I will be happy to answer any questions you may have.
So if there's any questions, feel free to write them in the chat. I'll remind everyone, so during Nathan's presentation, we did go ahead and post the link that has the online presentations available, so you can go to that website. We'll also include it in our follow-up email, as well as in the follow-up email, we will include audio. And then we did have one question, Nathan's asking, is the photo mapping offered as a statewide volunteer program?
Is this regarding the, I guess, the photo monitoring efforts itself? I mean, you could totally do it yourself. I don't believe there's any sort of, correct me if I'm wrong, but I don't believe there's any sort of official training to more details about photo monitoring. But we do provide a bunch of different resources throughout our presentations that you can do more research. But really just emphasize the importance of photo monitoring is that you're taking these repeated photographs at the same site over and over again. You're properly documenting where exactly that is with GPS coordinates or some sort of physical object, and also a map would be critical as well. But I don't believe there's a particular statewide volunteer program for photo mapping.
Are there any other questions? Dr. Jabber, did you get your, is your internet back working, or did you want me to open up the PDFs on my computer for the cross sections and the pebble counts?
Can you hear me? Yes. Actually, I did get my internet back, but it did cut off once. So maybe you do it through your website and I will talk. I can see what you're putting.
Okay.
That work?
Sounds good. Let me just get those PDFs. Which one do you want to start with, the cross sections or the pebble counts?
Let's start with the cross section.
Okay.
Very good. So this is the part where you guys get out your waders, but I'm assuming you don't have them with you now. So so the two activities we were going to do in the field today were, one, three activities actually. We're going to do a cross section, we were going to do a pebble count, and we were going to walk around the stream, look at a fast evaluation of the riparian area and identify a bankfull stage. But so we'll just go through the instructions for the two issues, and then at some point maybe we'll have a chance to do it in person. So the cross section, basically we use differential. Yes, can you show the pictures? Could you go up? Yes. So we use differential surveying to figure out the cross section, which means that we identify a random point that is easily accessible, and we do all measurement in reference to that point. So we're not really doing surveying compared to sea level elevation. We usually find a stable section, a stable position that we know whenever we can come back to, it will have the same elevation, usually maybe the base of a light pole or the edge or corner of a bridge or anything like that. And that would be our benchmark, which means it's a point of known elevation. The picture here shows a laser level system. There's a guy holding a surveyor level system, a guy looking into a level, and another person holding the rod. In our field work, we use the laser level, so we don't need the guy with the red cap backwards. He was annoying anyway. So we use a laser level that shoots a laser plane at that dotted line that you can see, and the laser plane will read on a receiver that we put on the rod the elevation from the ground to that dotted line. And so that the first reading we take is to the benchmark, so that's the point of known elevation. So where the guy wearing orange is standing, the elevation of the bottom of his rod needs to be, is known. We assume it's 100 feet if we're taking a random pole base, for example. We measure the elevation, let's say it's 100 feet. So the reading that the receiver reads on the rod, it's going to be the elevation of the laser level plane. Let's say it's 2 feet above the 100. So it's 102 feet based on our calculation. So that plane where you have these dotted arrows is 102 feet according to our calculation. Now we want to read the elevation to another point of unknown elevation. We call that reading a foresight. So let's look at rod position number 2. You can see rod position number 2 right there. You moved your rod to position number 2, and you take the receiver up to that level, and it's going to read that full distance right now. So the elevation of that new point at the bottom of the rod at position number 2 is going to be the elevation of the plane, which is 102 feet, as we determined in the first reading, minus what it is reading right now. So let's say it's reading 4 feet at this point. So it's going to be 102 minus 4. That point's going to be 98 feet. And so we keep doing this across the cross section. We move 1 foot apart, and then at the end we would have readings of elevations all across the cross section in 1 feet sections. You can go to the second page. And so there's a specific way you write these in your sheet, which would have been given to you in the field. So the elevation of the benchmark is 100. You can see, read the number 100 right next to benchmark right here. And we take a reading to the to that benchmark from wherever our level is. And that reading, for example, says 5. That means the height of the instrument plane, the laser level plane, is 105. It's 100 plus 5. From that point on, every time we take a reading to an unknown point elevation, we write those in the gray areas. So these are the 8, 8.25, 8.8, 9. And to get the elevation of that point, we subtract that. 8 minus 105 is 97. 105 minus 8. 105 minus 8.25 is 96.75, and so on. And these are all the elevation. In the first column, station, you usually put the distance that you've traveled between one point and the other. So you can see it's the first point was 0, then 2 feet, 3 feet, 6 feet, etc. And so now you have the distance and you have the elevation. You can plot it if you want to. One thing that we do in the notes, comments, and remarks is that usually we stop at special features like the left bankfull, left edge of water, the fellweg, which is the deepest point in the stream, the right edge water, and the right bankfull. So those, even if they don't fall on our incremental increase in 1 feet distance, we stop at them and take a measurement usually. And we note that this is why we did take that measurement in the notes and comments. Let's go at the next one, I think. At the bottom, there's the graph. So that we have an Excel software that will plot it for you. And that top one, you can see how that cross section looks like from bankfull to bankfull. And so the Excel sheet calculates for you the bankfull area, the average bankfull width, and the bankfull width and the average bankfull depth, and therefore it calculates the width to depth ratio, which we talked about a lot in the presentation as part of the classification. Then you manually measure the width of the flood-prone area, which is the double the elevation of the bankfull. So here you can see the depth of the bankfull is 1.2. So you measure 2.4 and you measure the width until you hit something at 2.4 feet above the bottom of the bed. And that's going to be your flood-prone area. In this example, it was 35, showing us an entrenchment ratio of 1.4. We will use that data for the classification. You can go back later to the presentation and look at that Rosgen flow chart, and you can do your classification accordingly. This is the sheet. This is all the different terms you can calculate. That's the sheet that we use, and at the bottom you can see all the different terms that you can calculate using the cross section or others. The one in blue here are the ones that are calculated directly from that Excel sheet. Other things need to be measured in the field, but that sheet right here shows you a lot of the different parameters that we like to measure in a stream that we'll use later in our restoration, the pool to pool, all these details. Let's go now to the next, the pebble count. So again, as we said, the cross section allows you to get all the information you need for the latter part of the classification. The number part of the classification is the substrate, which is the type of material, the channel material. And for classification, we usually do several cross sections that are representative of the number of pools and riffles in our reach. So let's say we have a reach that is around a meander that has 3 riffles and 2 pools. And so we want 100 samples from that section. So we would take 20 samples from each. So that would be 60 from the riffles and 40 from the pools. And so that's representative of the number of pools to a riffle ratio, and it gives us a good number that we would use for the classification. The way we do it, we go into the field, and again, we divide the riffle into or the pool into a very specific increment. So let's say it's 20 feet wide, and we want to take 20 samples. So we take one every foot. If it was 10 feet wide, we would take one every half foot. If it was I don't know, 100 feet wide, we would take one every 5 feet. And so that we want to take 20 samples. We walk into the stream, and we look away and go down and grab the first thing that our finger touches. That usually eliminates bias. If you're looking in the water, your hand will go to the bigger piece. While if you're looking away, it will touch whatever it first touches. You take it and you measure the intermediate ax on it. You see that graph in the handout. And so we measure the intermediate ax and we record it on the sheet. And so we would have 20 samples. Go to the next page. Let's go to the last one, and then we go up to see. So we would record those. You can see this one has one for has several, because you can do riffles, pools in this, and you can do several times the count. But in the first column, based on the dimension you measured, you put a bar or some way to count how many of these different pebbles you got in each different category. And then you can plot these, assuming an average size for all. I guess go down to page 2. We can plot them. We usually plot them on a log normal page. And you can see this is a logarithmic scale in the x-axis and a normal scale in the y-axis. You plot it, and at 50, that's going to be your D50. And that is the number you would take to do the classification. In this case, the D50 is 18.3, so that's 1.8 centimeters. That's going to be a gravel. So gravel is usually, I think 5. So this would be, is it? No, it's a 4. So it would be a 4 in this case. And that's basically it. Any questions?
If there aren't any other questions, Then I'll just remind y'all, so we will be sending this all out, but make sure you signed in on that Google Sheet that we posted at the beginning, so we know we can send out to everyone who attended. As I mentioned, we will still send out certificates, so you will still be able to submit for CEUs. They won't be as much as that we were able to offer for the full day, but you will still be able to get some CEUs. So you'll just need that abbreviated agenda I sent out in the email yesterday, and then that certificate. And then we'll make sure to follow, we'll send out all of those links we talked about. As well, we're gonna send out an evaluation. Following this, as we're kind of dealing with all of the uncertainties surrounding COVID-19, we're thinking we might have to offer some additional of these trainings online. So we'd love if y'all could kind of give us some feedback so we can improve these online videos as we need to. So just look for that in the email that we send out. With that, we really appreciate y'all tuning in today. We thank you again for your flexibility joining us virtually instead of in the classroom. Feel free to email any of us if there's a question that you haven't thought of that comes up a little bit later today or next week, whenever. We'll be happy to talk with you all. So,
And I had just, for the sign-ins you've even done some already, I went ahead and reposted it on the group chat page. So it's the most recent thing on the chat.
So I'll leave this chat open for 5 more minutes. So if you need to get any of the links we posted in the chat, you can quickly scroll up and grab them. I'll leave this open, but y'all are welcome to get some lunch, stretch your legs, and thank you again, and we'll be in touch with y'all soon.
Thank you, everyone. We appreciate it. Everyone have a great day and stay safe.
Thank you all. And yeah, send us an email if you need anything.